This video presents a brief introduction to the ideas of statistical inference and how to get information from a sample into a population of data.
However, we don't have access to the entire population in most cases. The population is described by population parameters which include the mean value mu and the variance sigma square, or sigma square root is the standard deviation. Since we don't have access to the entire population, typically we get a sample of n measurements, for example, and out of this we calculate sample statistics, which are the mean value of the measurements as well as the variance of the measurements. And then I should indicate the notation is wrong here. The typical notation is an S squared. The sample size is just the number of elements in the sample. In order to produce some information out of the sample that can be used in the population, we get hold of statistical expectation. And we can say that the expected value of the mean of a sample is the expected value of the population, and the expected value of the variance of a sample is the expected value, is the variance of the population. And so that's kind of the background behind statistical inference. We're not going to go into all details in here, but we're going to say that out of statistics of a sample, we draw conclusions about the population parameters with a certain significance level alpha, which is related to something called the confidence level C. Typical values of the significant level are 0.1, 0.05, 0.01. We correspond to confidence levels of 90%, 95%, and 99%. They are related by this equation or by this equation. The confidence levels for the mean of a population, for example, can be calculated or can be estimated given the mean of the sample and the standard deviation of the sample and a certain level of confidence or level of significance for the case of what is called a large sample, which is a sample with more than 30 elements. Those confidence intervals are given by this equation, where we notice the presence of a certain parameter, which is a quartile of the standard normal distribution, which is represented by a variable z, a random variable z that follows the normal distribution with zero mean and standard deviation equal. So let's talk about the probability distribution for statistical inference. These are used, for example, to construct confidence intervals, like the example we show, or in another application of inference called statistical hypothesis test. If we want to find, or we want to study inference on the mean of a population, on proportions of a population, or in the difference of means, we will use the standard normal distribution if we have a large sample and the standard deviation of the population is unknown, or for sample of any size is sigma is known. Or if we don't know the standard deviation and we have a small sample, we'll use the student t distribution. For inferences on one variance, we're going to use the chi-square distribution, and for inference on the ratio of two variances, we're going to use the F or Fisher distribution, those calculations. So the values of the quantile sought depend on the sample size, the level of confidence or level of significance, and the type of confidence interval or hypothesis testing that we are going after. For the standard normal distribution and the student t distribution, which is characterized by a parameter nu equal to the sample size minus 1, this parameter is known as the degrees of freedom. It turns out that the PDF is symmetric about 0. What that means is that, for example, you're going to get a figure like this, and you will be looking for quantiles corresponding to probabilities alpha over 2 in what is called a two-sided case. If we have a one-sided case, we're going to be looking for a quantile whose probability to the right is equal to alpha, or one whose probability to the left is equal to alpha. These two last cases will be referred as the one-sided cases. Here we repeat the figures of those three cases, and we're going to now discuss it in a bit of detail. For case one, we have a two-sided case where we split our probability, or the level of confidence, the significance level, into half, and we put half of that significant level in a probability to the right and a probability to the left, alpha over 2. But because of the symmetry, we only need to calculate this one, because this one is going to be the negative of the first one. And so the typical notation is that we give the probability of z of alpha as the probability that z is greater than or equal to z of alpha, which is 1 minus alpha. And so the subindex z in here is related to being greater than or equal than z sub alpha by this amount. And so for case one, we're looking for this situation of probability. Oh, actually I made a mistake here. This is just equal to alpha. And so if we have that case, we look for z sub alpha over 2 by having a probability equal to 1 minus alpha over 2, and we take the inverse cumulative distribution of the standard normal. By the way, for the standard normal, typically the PDF is referred to lowercase phi of z, and so the CDF is uppercase phi of z. So here we will be taking the inverse cumulative distribution function of the z distribution. And in a similar fashion for the student t, we're going to use a inverse distribution of the student t distribution, but the concept will be similar. We're looking for a certain value of t sub alpha over 2, so that the probability to the right is alpha over 2. For the case 2 is a one-sided case. We're looking for a probability whose area to the right is equal to alpha, and this probability right here. Inverse function, or I mean, talking about this using the CDF, we have this situation here, and the corresponding value will be the inverse cumulative distribution function of the standard normal of 1 minus alpha. And in a similar fashion, we will calculate t sub alpha if we are dealing with the t distribution. Remember the symmetry of about the zero value. For the case of a one-sided case to the left, then we're looking at probability that the z less than minus z sub alpha equal to alpha, which means phi of minus z sub alpha equal alpha. Minus z sub alpha is going to be equal to the inverse of minus 1 of alpha. And so in a similar fashion, we can calculate the negative t sub alpha for the student t distribution. For the chi-square and f distribution, the quantiles that we seek will be more complicated because the fact that the PDF is non-symmetric. And so we have one case where we split the significant level alpha in half to the right and half to the left. And these two distributions, chi-square and f, are such that are defined only on the positive side of the curve, of the axis, sorry, of the x-axis. And so this is the case for when we split the area. This is the case for the area to the right, and this will be the case of the area to the left. It's in here, and we proceed to discuss them in detail. For case number 1, we're looking for actually two parameters. One that we're going to call chi-squared of alpha over 2, and one that we're going to call chi-squared of 1 minus alpha over 2. Remember that the subindex is related to the area to the right of that particular value. And so for the first case, this would be the inverse value that we're looking for the one to the left, this quantile, it will be equal to this. A similar way we're going to do that for the F distribution. And so we are going to be using the inverse cumulative distribution function of the chi-square or of the F distributions to calculate those parameters when the graph is non-symmetric. This is a one-sided case number 2, where we are looking for a probability that the random variable is greater than chi-squares of alpha. That means we're going to be dealing with the inverse cumulative distribution function of the chi-square for 1 minus alpha. And when we're looking for the one-sided case to the left, we have the probability of the variable being less than x of 1 minus alpha. Chi-square 1 minus alpha is equal to alpha, which will give us this inverse cumulative distribution function. In summary, when we use the statistical tool plugin, we're going to be using the ICDF normal inverse for zero mean and standard deviation 1, the inverse for the student tuition, the inverse for the chi-square, and the inverse for the F distribution, where we're using this P prime as the first parameter that indicates the probability, and that P prime could be equal to any of the values shown down below here. And with that, we conclude this particular presentation.